Hi, welcome to the Ethereal Mechanics Foundation Series Rhombus Experiment Data Review. This is a general audience. My name is Robert Distinti. I'm an electrical engineer with over 30 years experience. You might even say I'm a disgruntled engineer, but all right, I forgot to change the introduction. But the introduction, what we're going to do is review the data and the software for the Rhombus experiment. This is a screenshot of the software when you boot the software or load the software, run the software. This is what you're going to see. In this box here is where you enter the experimental data, and you don't have to worry about entering any data. These three buttons here, 97, 07, and 15, if you click either of those buttons, it'll load the experimental data from 97 or the experimental data from 2007, which is when I did my graduate thesis, or the data that was taken on the video that supports this video series. If you click that, it'll load the data into this area up here. There's two different function sets. All, we're going to do all first. The abbreviated function set is just a few that I know work out, and the idea is we can do other experiments without having to go through the entire set, which is significant. This box here shows you, if you select this, how many number of different geometries exist in that set. Delta L, that's that's the delta length of the wire, how finely it's being chunked, I guess, fragmented is the better word. The maximum RMS error in nanohenries, that is when the software is searching if a geometry gets the experimental data within 10 nanohenries of RMS error, it'll add the candidate geometry to the output list, which is here. Ignore same-side linkage. We'll cover that in a minute. For the initial, just keep that unchecked. We're going to do all. We're not going to ignore anything. All right, so the first thing we're going to do is we're going to select all. And we're going to change the delta L to 0.4 to speed it along, 0.4. Oh, we're not going to be ignoring same-side linkage. Got to keep that unchecked. Okay, so that's what we end up with. When we select all, there's 9240 number of different geometries. Here's the data that you get when you click the 15. That's the data from the experiment. I hope you can see it with the resolution of the camera. When you hit the search button, this search is going to take probably 30 minutes or an hour, depending on how fast your computer is. There's a progress bar here that we'll show you when it's complete. It's not going to dump the candidate geometries out into here until it's done. And now what you have here is, this is the candidate geometry. This is the RMS error of the data. When it calculated, it went back and used the derived constants and computed the shape values. Okay, and then what it did, it is RMS of those. It only shows the first four shape values here. You can have any number of shape values in here that you want, but it's only going to show the first four computed inductances of the first four shapes. And this is just a simple text description of what this geometry over here means. Now, what we had here, when this was computed, there were 62 solutions that came out within the 10 nanohenry max RMS error. Now, the way we're going to process this from here, now, if you right-click, you're going to get a box, and it's going to give you the option to select all. Okay, and that's going to select all the data. Or you can select, you can use the standard window controls to select just what you want from here. Okay, once you select it, you do a right-click again, and it'll give you the option to put it into comma-separated value on the clipboard. Once you do that, you can dump it into Excel. Okay, from Excel you can do all kinds of sorting and stuff. I could have put it in the software, but I don't want to waste too much time writing software if it's already there in Excel. The first thing we're going to do, we got 62 solutions that came, and this is interesting. We got 62 mathematical models that fit the experimental data within the measurement accuracy, which I'm estimating to be 10 nanohenries. I mean, that's just phenomenal. Okay, but what we can do now, we can eliminate certain ones, especially the first ones that have negative constant. Column F is where the constant of relation is going to go. And if you notice, the geometry 5099, which we're going to eliminate, comes 1 times 10 to the minus 7, but it's negative. So we get the exact correct answer as far as where the ballpark of what should be the constant of relation. But because it comes out negative, it means that inductance is negative, which basically is an over unity solution. So the first thing you're going to do is go and clip out and condense the list and get rid of all the negative solution. That leaves 26 solutions. And of these solutions, the ones that have zeros, which means they are not affected by distance, is not reasonable. It's got to be affected by distance. The answer has to be affected by distance. And the ones that have a distance in the numerator means that the energy increases over distance, which is over unity. So we can basically eliminate any geometries that have in their first geometry column a 0 or a 1. And then that leaves 8 solutions, which are here. The other thing we can do is, using the rule of acquisition number 17, ambiguities for mystics, we can eliminate the cosine squared solutions, because those end up in ambiguities. Okay, so any of these here, like for example, this is cosine TASA times cosine TSA. So this is a cosine squared solution. Here was cosine squared right there. And if you go down and eliminate all those, you end up with 2 solutions. The 2 that actually fit the data the best. And it's interesting, this is 5008, which, I already know that's the answer, but we can't make that assumption now. We have 5079. Both of these are very good as far as their accuracy within the experimental data. The constant of relation that's derived is dead on, because we expect for Km, we want 1 times 10 to the minus 7. We're essentially getting that. That's probably just experimental error that it's not exact. And these are the basic geometries. So what do we got here? Well, one of these geometries, 5008, is a spherical field. This little symbol represents an accelerating charge. From that accelerating charge, the energy is uniform in all directions from the accelerating charge. Beautiful, simple, spherical field. I love it. But, we can't let our concept of beauty and simplicity override what, is the scientific truth, or the best answer that best fits the data. Okay, the other geometry that we've got is what I call longitudinal field model. From the accelerating charge, it's in front of the charge and behind the charge that's affected, not to the sides. So the way you can view this is if you took a balloon and you constricted it in the center, okay, that's what the field looks like. But the interesting thing is neither of these are the B field from classical theory. If you recall from the first experiment, we went over the B field, the Biot-Savart model from classical theory. The Biot-Savart model is a transverse field. And the way you can imagine that, if you take a balloon, I wish I had a balloon, it would have made this a lot easier, and you push through the center of the balloons until your fingers come together, you're going to get a donut-shaped field. Okay, and that's what this looks. This is like a cross-section of that donut shape. It actually goes around, and this is cross-section. And so this is a transverse field because it's transverse to the direction of acceleration of the charge. Transverse means it's to the sides of the accelerating charge, whereas a longitudinal is to the front and to the back of the accelerating charge. And the spherical field is uniform in all directions. None of these answers is the B field of classical theory. And the interesting thing, though, is if you sum the transverse field model and the longitudinal field model, you end up with the spherical field model. Okay, that's an interesting thing. We'll come back to that in a later video. Okay, but what we have to do now is we still have to, we still have to disambiguate which one is the correct one for self-induction. They both give the same answer. And we're going to do that in the next set of videos in the foundation series. But at the very least, what we can say now is a B field of classical theory at least is an incomplete representation of a magnetic field. Okay, now for now though, let's tie up some loose ends from the quad loop experiment. Remember the paradox from the quad loop experiment. The derivation done by the classical physicists came up with an inductance per unit length of mu naught over 8 pi, which works out to 50 nanohenries per meter, regardless of the diameter of the wire. And this is a paradox because the mu naught for free space by itself is 1250. I mean, the inductance per unit length of free space is just mu naught, which is 1257 nanohenries per meter. And there is nothing in the world of physics except superconductors, and we're not dealing with superconductors, and that has a relative permeability less than free space. Yeah, okay, you know, copper and some other have 0.9999, something like that, but that's essentially 1. Okay, it's definitely not a difference of 1257 to, you know, a difference of 8 pi, of a factor of 8 pi. It's subfractional. It's very tiny. So this cannot be the correct model. There's no way that a derivation for inductance for wire can come out less than the permeability of copper itself, which would essentially be the permeability of free space. So what we're going to do now, let's see what the experimental data tells us. Okay, the inductance per unit length of wire can't be less than that of free space, but it can be greater. I forgot to mention that in the previous video. It can be greater. There's a lot of materials out there that have greater relative permeability than free space. But other than superconductors, none have less, unless it's like copper or one of those other metals that was very, very slightly less. But so let's use the experimental data to determine what the inductance per unit length of the 22 gauge wire is. So what we're going to do is go back to the software and we're going to check the box. We're going to use the abbreviated set. We don't want to go through the whole geometry. If you want to go through the whole geometry set, you can do that. Let's just click the abbreviated set. And we're going to ignore the same side linkage. Okay, and then we're going to click, compute. Now what are we doing when we're ignoring the same side linkage? Well, the software normally takes each fragment of wire and computes its effect to every other fragment of wire and does this all the way around the loop. But if you remember the derivation for internal inductance, that was supposedly taking care of the effects of the magnetic field that never leaves the wire. Okay, so this little loop from here to here is a misnomer. That magnetic field actually goes through the wire. Because that little amount goes through the wire, it's still internal to the wire. It doesn't really jump around. This is just easier to show it that way than it is to show an arrow through the wire. So what we're going to do, same side linkage does not compute the fragment to fragment effects within the linear section of wire. It only computes it to the other three sides. Therefore, what's going to happen with the software is the shape effects are just going to be the effects from across space. And what's going to end up in the constant, because the perimeter of the wire doesn't change, the constant in the equation is going to end up being the internal inductance, because that's going to be left over from the linear regression as we talked about before. So what's going to get stuck in the constant part is going to be the inductance that is due to the 72 inches of wire that's in the perimeter of the shape. Okay, and this came out. This is the actual result here. And we're going to use geometry 5008 because I'm already sure that that's the right answer. And it comes out to 2625 nanohenries for the 72 inches. So we take the 2625 nanohenries for the 72 inches of wire, and that's approximate. I mean, there's other, there's lead inductance and the little loops at the corner inductance, but let's consider those negligible. So if we take the 2625 and we divide it by the 72 inches of wire, multiplied by 39 inches of length in a meter, 39 inches per meter, that gives us the inductance that's internal to the wire is 1422 nanohenries per meter. And we compare that to the 1257 for free space, and we're good because as long as we're greater than the inductance per unit length of free space, we're golden. And it's a far cry from the 50 nanohenries derived from classical theory, which is a contradiction because it can't be less than this unless copper is a superconductor, which it is not. So let's compare the old to the new. In the old classical derivation, the internal inductance for a 72-inch rhombus or a 72-inch perimeter of wire is going to be 92 nanohenries, just from the perimeter. And the area, supposedly, should be the remainder, which would be 2366. But we don't get that with Faraday's law. Faraday's law bombs on the answer, doesn't give us an answer. But if classical theory were correct, and the internal inductance theory model were correct, then the remainder of the inductance due to the area would come to be about to be 2366. Okay, and so what we have, if we want to put it into an equation form, is the total inductance is some function of area plus some function of perimeter, where the area is the dominant contributor. Okay, now if we look at the new induction model, we find that it's completely backwards. The internal inductance is the dominant factor, which makes a lot more sense. And the area is actually a negative contribution, which makes a lot more sense when we actually look at what's going on for induction. And so there, what we find out, though, is if we make this area larger and larger and larger, this contribution from area becomes less and less and less. And therefore, if we put this into an equation form, we find that the inductance due to the perimeter, okay, is the internal inductance, which is the first one I've listed here, is a function of the perimeter and inverse and 1 over the diameter of the wire. So here we find the diameter of the wire also has an effect, but an inverse effect. The thicker the wire, the less inductance. The longer the wire, the more inductance. And that's what this means. And we find that the contribution to the area of the loop is an inverse and a negative. The bigger the area, the smaller the effect, and it's negative. So the irony is that in classical theory, the internal inductance is minuscule, whereas in new induction, the internal inductance is dominant. See how we got stuff, we always get stuff back, but and you'll find out when we get there that 5008 does all of this. And it comes out with very accurate answers, very conceptually simple answers. None of this jumping through hula hoops with this classical theory where you need Biot-Savart, Faraday's, Lenz's law, and the internal inductance model, which is not any of those. Okay, so we're replacing everything with a simpler model that does everything, and it gives us good answers. Gotta love it. So what's the next steps? We need to disambiguate between 5008 and 5079. Or we got to do something. It's either one or the other or both or something. We got to disambiguate. And then we also need to answer the following question. How does the partial inductance model and the Maxwell mutual loop approximation, which isn't self-induction, it's mutual induction, give such good answers if they were derived from classical field models, which is a transverse model, which does not even show up in the experimental results? How did that happen? How does that happen? Well, you have to tune in later, folks, to find this one out. The software will be released in the next few days. I'll send out a notice to subscriber. A link will be placed on the video page once it's up. Now for the tearing ceremony, the part you've all been waiting for. Dun, 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 dun. What we're saying here at this point is the B-field model is an incomplete model. So we got to go remove everything related to the B-field. Okay. First part of this book is vector analysis. Okay. Vector analysis is obsolete as written here in this book. You go look at Q vectors on my YouTube page. There's a course on Q vectors, not complete. I still got more parts to add to it, but Q vectors is going to replace standard vector analysis, and we need to do that as we get deeper into electromagnetic theory. Because this is still useful, even though it's obsolete. In other words, there's nothing really wrong with it. So, and it's not, and for what it is, it's complete, except that it's missing a vector division. So I'm not going to tear this out just yet. Okay, then we get to electric field. Coulomb's law, well, it's not really a law, it's an empirical model. Idiots call everything laws. They're not laws. It's got an arbitrary constant relation. It's an empirical model. I don't know why they think they have to call everything laws. Okay, so we get here, we say flux density, Gauss's model, and divergence, no problem. No problem. Energy and potential, no problem. Current and conductors, no problems. Dielectric capacitance, no problem. Poisson and Laplace's equation, no problem. Method of images, no problem so far. Okay, steady magnetic field. Steady magnetic field. And Biot-Savart. Time to go. Magnetic forces of materials and inductance. Time varying fields and Maxwell's equation. Go look at my video 2 and 3 of the ethereal mechanics introduction videos, videos 2 and 3. You'll find that this is in violation of Kirchhoff's law, which is del cross E equals 0. So this is bunk. And the displacement current causes over unity. Those are in the first 2 videos, so these are garbage. This guy here is okay, but he's already in the part of the book that I accept, so it's unnecessary for him to be here. Transmission lines, that's okay. That's just circuit theory. I got no problem with circuit theory. And these are just approximations anyway. Okay, then we come to, okay, the uniform plane wave. This is complete and absolute bunk. Okay, but I'm going to save this for later. We're going to have a lot of fun with this. When I do the Distinti course on wave theory, I'm going to show you that this is complete and utter bunk. And for you engineers out there that say, no, we get good model equations with it, look at what you're using. You guys are using e to the j omega. Or e to the j omega. Okay, that's not Maxwell's equations. Okay, we'll cover all that. This is basically Euler's equation. And it's also the kernel of the discrete Fourier transform. And radar guys use this to great accuracy, but this is not this. Okay, but we're going to pull this out when we get to the thing on waves. So we're going to save this. We're going to have fun with this later. So, but that's going to be going. All this stuff. We've got wave guides. That's going to go away too. But we're going to have fun later with that. And what else we got here? Appendix B, units. Okay, Appendix A, vector identities. Vector analysis, a little obsolete, but still useful, so I'm not going to. Material constants, Appendix C, I don't really have a problem with that. So that is where we are right now. Okay, we tore a great part out of this book, and when we get done, the rest of this is going to go away. And when we get to the end of ethereal mechanics, this part's going away. So that's where we are right now. Thank you. No more voodoo physics. If it don't match observation, it ain't worth crap.